Hey, hi everyone. So today, in continuation to what we were been studying, we studied on intro to AI. We studied on machine learning, and then we started with few of the top algorithms and machine learning. We understood what is we understood what's the purpose of whole bringing up this algorithms, and how does this algorithms help in learning, which in turn learning in the form of training, and after that learning how it is converted to intelligence, right? That's the journey that we want to get into. We have data. We should build an algorithm which has some training through which it learns, and then using that algorithm which converts into model. It sees future data that is unknown, and basing on the unknown data, it will predict some values through that intelligence that it acquires, right? This is the flow. So we discussed on the um, machine learning. We discussed on what are the algorithms, how does the pattern recognition work in day three, and how does the what is the approach of building these algorithms to some extent, it's been discussed. So that being all generalized topics, and those are foundational for understanding today's discussion. But let's get deep into linear regression today, and how that has been implemented, and how that really worked, and stuff. Um, so I'll take you through a journey which will actually help you on how it would have evolved, so that people understand in a much better way. Usually, when we read a book, we think that okay, this somebody very smart sat in a room, and they are like, okay, pick up a paper, and then they started writing everything. Usual experiments, innovations, discoveries don't happen like that. People start off with very vague, small, little bit thing. Mm, Maybe like, okay, machine learning, I'll just have all the data, I'll just draw one line, and yeah, that line actually helps in predicting what will be my future values. It'll be as simple as that. They start there, they don't come up with all possible issues that it could get into and stuff, right? So they start with a vague thing, and then they try to do it. They see some challenges, they'll fix them, they'll see how they're fixing it, and then they think of how I can automate it. So it's an evolutionary process where it refines and then finally comes out as a thing which sounds very complex for us, but that's a few years worth effort that goes into it, so that it comes into what we see. And obviously, because somebody has worked on it for certain years, their insight and effort of it makes it little complex. But if you dissect it and understand it, look through that on what is the purpose of implementing each of them, you can connect to it pretty well, and it will help you a lot in implementation, because you not only know what it is, you understand the thought process behind why something like that is being implemented. Okay. That being said, um, I'm assuming everybody's set with what kind of thinking that we need to go through. Let's start off with linear regression pretty quickly. So, as I explained yesterday, so linear regression. Let's see. I also want to see, does this whole YouTube live? I don't think it provides anything called a whiteboard or something like that. App icon window, and then okay, fantastic. Fine, let's not waste time and then get started with our document. Okay, so here I thought I'll cover these, but most probably I think we today I I relooked at things and thought, okay, um, I know it takes more time. People need patience to understand this whole thing that we're trying to say and all that. But while we say it, while I say all that, one second, sorry guys. Now this will not pop up. This this become a problem, man. This has become problem. I don't know. I should solve this again. If I share and then I open this, it'll work. Yeah, it works. So what I want to do is I want to get into the detail on linear regression, so that people are on board here, because I so for this day is very very important. I want everybody to understand it better, uh, so that we have the foundational knowledge, and we travel together, right? So what happens, we can you guys can we can start with day 5. There's nothing wrong about it. People are smart enough that they can pick up and understand things from there, but the way you interpret the things that we communicate with each other will not be the same until unless we have a common understanding, like language, right? Whatever words I'm speaking, you know the language, you know what I mean when I say something. So we both communicate to each other. Similarly, in machine learning also, foundational knowledge, if we are not on the same page, we are not on the same thinking, the capacity of understanding or the perception of what we are reading will be completely different. So on that context, I thought, okay, let's spend a couple of days more and then get to the detail. Okay, that being said, let me get into linear regression. So yesterday we discussed saying, given there is some data, and the data is represented by certain features. Okay, so for now we'll assume saying the data has been already given in a format of features, like feature 1, feature 2, feature 3, kind of stuff. So I'll call them features as x1, x2, x3, x4, x5 kind of stuff, right? So, and then what are we trying to derive, right? The inference or slash prediction will be y, where so so you should look at it as like a tabular format, right? Like the x1, x2, x3, x4, so on will be in the columns that are there, and then y will be in the one of the columns which is output actually. So if x1 is this, x2 is this, x3 is this, x4 is this, then y is equivalent to this. That's how you get incoming data, and that could be depending on your use case, availability of data and stuff you gather. You how many ever records, like few use cases you don't have data, like healthcare and stuff, maybe you would have hardly handful of data, like maybe 10,000 records, something like that. And some go to financial banking and stuff, maybe you'll have millions of records. So the data set size varies from place to place. Okay, now as I said, so coming to linear regression, what it does is it tries to put together a either a line, or it tries to put together some shape, um, some form of a pattern that it draws, basing on the points that are there and how they're distributed on the space, which will actually, that line is our assumption, saying, if I pick a point on that particular line which actually represents all these x, then this, so if you take space, if you take axis like this, and if I put all the x points like this, if I draw basing on linear regression is nothing but, you should remember, it's an equation which helps in drawing a line, drawing a line of different shapes. So I'm not saying straight line, it could be a curved line or whatever. And that equation is used to, that equation is nothing but, actually that equation is our algorithm. So, um, what happens is that line is what is connecting in between x and y, right? So, for example, if you draw a straight line, right? And anyways, it could be anyways. So it's like y is equal to mx plus c, right? So on that line, if you, for a given x, what is the corresponding y, right? This is x. It comes here. The line is here, and this is corresponding y. How do you see the value of y at a certain point, like x, mx plus c, m, value of x, m into x value plus c. If you do it, you will get the corresponding y value. Agree? So that's how equations are made. Like given the input x, you put them into an equation, you calculate the output is called y. Correct? Simple. So similarly, what you do, basing on his x points that are there, you think of it like, let's say, as I said yesterday, if all of the points x1, x2, x3 are like 1 comma 1, when I say 1 comma 1, 1 is x and y is 1. So 1 comma 1, 2 comma 2, 3 comma 3 or something like that, then a straight line would represent it. So tomorrow if 5 comes, obviously it is 5 comma 5, because y is equal to x is the equation through which this line is going. So 6 comma 6, yeah. So I can predict it, and I assume that, again, there is always an assumption basing on the data that we have. I assume that this particular line will actually predict my y values for the unknown x that I see in the future. Correct? Is it correct? Is it wrong? We don't know, but we are doing it basing on the pattern that is there in the current data, and we are assuming that it will be the future data will be in similar pattern. Okay, so is it 100% correct? No, because it might not be, because people don't know extensively what is the kind of the data that they are exposed to, and if they know what kind of data they are exposed to, they need not come in for, they need not opt for machine learning approach to solve that problem. They can go for typical application driven solutions. Okay, I think this pattern and everything I've already explained it yesterday. I'm spending a lot of time again repeating it because I just want you to guys to be very clear. But it need not. Okay, I gave you an example of straight line, but it could be also a curve which has maybe like x1 x2 plus x3 square plus x4, any combinations, right? A polynomial with different degree of polynomials with or something. So you can come up with a different equation, and as long as that equation helps us for a given x to predict y, that is actually the right algorithm that we want to use, and that's what is the algorithm, and which eventually becomes the model which predicts y. That's it. So did I make it very simple? I think so, but that's the right thing. And if you look at the whole machine learning algorithms, models, so-called complicated terms, it boils down to simple math, and it's a math equation, especially talking about this linear regression and stuff. But even if you go to complicated things tomorrow, like let's talk of decision trees, let's talk of random forest, let's talk of um, SVMs, let's talk of neural networks, let's talk of transformer architecture. Anywhere you go, there are different approaches, different kinds, and all that stuff. But everything boils down to a mathematical equation, where the objective of the mathematical equation is to derive y basing on x. Okay, the representation will be different. The um, the instead of using one equations, maybe we'll use multiple equations. um, the combination of equations um, are there are different approaches on how the equation needs to be derived. um, how see, like as I said, x1 x2 x3 x4, you can have multiple combinations. Like I can say w1 x1 plus w2 x2 plus w3 x3 is equal to y, or you can say w1 x1 square plus w2 x2 square plus w3 x3 square is equal to y. That's also possible. So there are multiple possibilities. When I say equation, it could be have n number of permutations and combinations, right? You can just simply say x1 into x3 into x4 into x5 is equal to y. Everything is possible. So the complexity comes into what is the equation, the right equation that I put here, which aligns with the x data that is there, and also gives me proper y. Okay, deriving this is the most complicated thing in the whole machine learning journey. And the equations need not necessarily be linear. As I said, they are, when I say linear, the linear equations are the one which fall under this linear regression. And similar things will also be used in logistic regression. Similar things will also be used in the neural networks. So there if that's the intent of calling it as a linear regression. Okay, we should be clear on it. But how? So let's get to the detail on how do we start off. Okay, so because we are talking about 1 million records, if there are three records, and if the three records are x1, sorry, x1, oh, why is it going caps? Okay, maybe the no, x1, oh, okay, whatever, x2 and y. Okay, and let's say if it's 1 and 4, or let's say 1 for simplicity, I'll say 2. Okay, this is getting into the tabular format. That's the challenge. Why is it okay, 1, right? So similarly, let's say 2, 2 and 2, right? So 4, 4, 4, something like this. And x1, as I said, typically people take linear regression, they take only one x so that people are not confused or something like that. But I want you guys to be realistic. There is never saying, okay, given one x, predict y. That's easier, right? So there's always multiple features, and if there's one feature and then that that you know of a product, and then you want to try to predict y, it's a simpler problem to solve. But the scenario is always you have multiple features. But how do you deal with it? As I said, so if it's like this saying, uh, this is x1, this is x2, and you want to predict y, so it's three dimensions, right? The x is a different dimension, x2 is different dimension, y is different dimension. What we do is we bring in we project the x2 onto the x1 surface. That is, the values that are there like this, the equivalent value of it will be projected into the x-axis here. So we combine these values like this and bring both of them to same plane, assuming, again, it need not necessarily, because it depends on the scale of the values, because this is complex and important. It comes in when you do exploratory data analysis and initial data processing and stuff. This could be the um, this could be the width of the, if you're talking about a table, right? So a table has legs, and then it could be width of the legs. So it usually would be in centimeters or inches, right? This could be cost of the table. Okay, so this cost of the table could be in 200 $300 and stuff. But whereas if you are counting it in here in inches, it will be less than 10 inches or something like that, right? Far less than 10 inches, because we're talking about width of the table. So when you project it, what happens? The width is here in the x-axis, right? It will be 0 to um, 0 to 4 or 0 to 5, whatever. But whereas the prices could be varying high here, right? So what we do is to project it here onto the same plane, we bring them to equivalent values. We scale them down so that both of them are on equivalent values, so that they can represent it in the same space, and those values could be mapped to y seamlessly. Or else, if what happens, let's say you have the width of the table in 0 to 5, and the price ranging in 100 to 200 or something like that, or 50 to 200, kind of something like that. You can't practically put an equation which will actually say, okay, for the line will go like this. And so let's say we want to do a straight line. It's impossible, right? Because few of the x are here, few of the y are here. You should draw a line like this, which doesn't make sense, right? Because both of them are far apart. So what we do usually is, that's not an important topic now, but just because we are having a context and explaining, but we can go into the detail when we solve some problem hands on sometime later. But we bring down this x, we scale down both of them to one level, so that all those points are here. So it's basing on scale. So like for example, if the range of it is 50 to 200, I'll make 50 0 and 200 as 10. So or 200 as 1. So what will happen? All this 50 to 200 points will boil down to 0 to 1 range. Similarly, what I'll do, this 0 to 5-inch width, I'll scale it down to 0 to 1. So what happens now? In this space, I have everything in between 0 to 1. It's your choice. You can make it 0 to 10, anything. But if I scale it down to 0 to 1, all the points are in same space. Now if I draw a line, everything goes through the same points. Agree? Or if I put an equation, any equation, I have similarity between them. That's how you bring down everything to 1x. So x is you can actually look at it like capital X. Here I should somehow make it 1x. Capital X, I mean, just for representation purpose, I can say it's a combination representation of x1, x2, x3, so on. Okay. Now let's talk of picking up something, right? So next thought process is, okay, I have x, I have y, I want to understand the pattern. I want to come up with a pattern which will actually map the given x to y, and there are a number of possibilities, correct? How do I make a choice what to do? Like, how do I make a choice on what equation to use? But let's start with somewhere, right? Because if you start, that's a complex problem, saying, okay, should I put a line, polynomial, what degree, how, what combination, x1, x2, x3, x square plus x cube plus x. The list is exhaustive. You can have, there are millions of things that we can think of when you think of something like that. So the question comes is, let's start off with something, and let's take baby steps on. If I start off with something, okay, as a random choice, so how far that will work out, how far that's the right thing to start off. Okay, let's say we'll make it very simple. We'll assume that like the points here, right, these very much indicate for me saying, yeah, there could be a linear, I can put a straight line and I'm good with it. I can predict values basing on it. Okay, so what I'll do, I'll put a straight line. Okay, now I'm looking at these 3 points. Basing on these 3 points, I can actually say it is a straight line, which is more like y equal to x, kind of a straight line, right? um, or it could be y is equal to wx, uh, w1 x1 or something like that, right? So we don't know, it could be any, but it could be a straight potential straight line, right, which will go through these points. Now when I put this straight line there, how do I decide that straight line is the right algorithm for the given points? So for example, let's say I pick up a line, random line like this, y is equal to 3x1 plus 3x2 plus c. I can't say c, I should have a clear value for it. Let's leave it like this, like 3x1 plus 3x2. Okay, now what happens, if I go start putting these values here, so this is y that is given to us, and this is my y that I'm predicting uh, through my equation, right? The equation, expectation of the equation is it should be able to predict this y, right? So here, if we start putting up values into this particular table, what happens? So this is y, and let's say this is y predicted, right? So I'll put small p, okay, and what will be the value? So if 1 comma 1 is put in here, the value is 6. If I keep 2 comma 2, it becomes 6 plus 6, 12. If I keep 4 plus 4, then it will become 12 plus 12, 24, right? So the actual expected value is 1, we got 6. Actual expected value is 2, you got 12. Expected value is 4, and you got 24. So what does it say is, okay, as I said, people would have started like this, right? They would have thought, okay, why not just pick some number and then equation, and that will predict it. But they would look at these values, and for you, you feel, yeah, it is wrong. Yp and y are not matching. The expectation is y and yp are not matching. So, but these three things, because you're looking at it, you're able to say, but what if there are million things? How will you look at them and say they are right, wrong, or something like that, right? It's not possible. So uh, what would people do is, they don't have another choice, but they say, okay, there are million records, but how many of them are matching and how many of them are not matching? First thing, right? Okay, for those are matching, good, we did a good job, our algorithm is great, it's doing good and stuff. But for things that are not matching, what is the difference? Okay, what is, how much is the difference, right? And what should we do about it? For example, in this case, if you look at what is the difference, it's expected is 1, it gave 6, so 6 minus 1 is 5, and expected is 2, you got 12, the difference is 10. Expected is 4, you got 24, that difference is 20. So that's the difference, right? uh, so the difference that we see here is actually because of picking up this specific equation. The difference that you see is actually not a difference between what is should be actual value of y and what is the predicted value of the y. That difference is nothing but the loss of y, right? Y is supposed to be 1 and it became 6. So you should look at it as the loss is 5. Similarly, for 2 and 12, the loss is 10. For 4 and 24, the loss is 20, right? So what we need to do, if the loss, we need to try to reduce it. Agree? So 1 and 6, if it, if you, it is 5 now, if you reduce it to 4, if you reduce it to 2, 1, and something like that, the loss is smaller, correct? So you're coming closer to, so the gap in between y and yp, y predicted, you should reduce it as much as possible, so that yp is closer to y, or yp is same as y, so that the prediction is what we are expecting. So this is what the difference is called, loss. Okay, so that loss is calculated like this. So people say there is a loss, there is something called a loss function. So again, where we are heading, instead of simply understanding all this and all this and stuff, your thinking should go, how far is yp from y? I want to find out, so that I can make a decision, right? Saying, okay, yp is this far from y, so now I say my current equation is this bad. It's like, you have an algorithm, you have a machine learning model, and that's this bad. If you classify it, you know how much it is bad, you know how much to correct it, correct? If you don't know how much it is bad, you can actually assume, saying, okay, yeah, 3x plus 3x1 plus 3x2 is perfect, it fits in perfectly into what I'm expecting, so I'm all good. No, you are not, right? It is not correct. So because the um, loss shows me, saying the loss is high, right? And again, that's another thing that people should think about. How does somebody predict loss is high or loss is low? So we don't know. All we try to do is reduce the loss. At some point, we should agree, everybody should agree, and loss making loss zero is also not the right thing, because we'll discuss more about it later on. I don't want to give you more things at this point of time and um, complicate things, but let's try to make it as simple as possible, right? So this is loss. I want you guys to understand what the loss is. And so for in this case, loss function would maybe say, um, we can say sum of diffs above, right? But what would happen is, what if the points are negative, right? Minus 3, minus 3, and let's say minus 3. Then what happens? Your yp is minus 18. And if you see minus 18 minus 3 will become minus 21. This looks like the difference in between the loss between minus 3 and minus 18 is minus 21, but actually it is not, right? Okay, my bad. Minus 18 minus minus 3 is minus 15. Okay, so minus 15 looks like is actually the loss. But if you look at it from individual row, it is correct. But when I do the sum of difference, what happens is the loss of this function will become 20. 5 plus 10 plus 20 plus minus 15, minus 15 will remove 10 and 5, and then 20, right? But and this appears like it has lower loss compared to only having these three rows, correct? Are another equation, because this is not correct thing. Because so what people do, sum of the above loss function doesn't give you the actual loss. So this is not good. So we need to represent it in other ways. One way to represent it is, we can go for we should go independent of the problem that we see here is, there are signs, so plus and minus, so we are looking at plus and minus there, counting them as plus or minus doesn't make sense. So let's just um, get rid of the plus and minus, right? Like we apply a modulus operator and make them all plus. So like you can say mod difference, right? So then what will happen is mod difference is 5, 10, 20, 15. Okay, so this makes perfect sense, right? So now the sum is the sum here. In the previous case, the sum is actual loss, the sum is 20, but now in the new, if you apply mod on top of it, the difference is the sum is 50. So this is shows my loss in a proper better way than the other case, because the other case is deviating from the actual loss that is there, kind of stuff. So this is lost function. So which is good. So these two, I think we are clear on what is the loss function, right? But let's say these two records are not there, the 20 and 15 is not there, then the loss function value is 5 plus 10, 15, correct? What if I have 3 records? 35. What if I have 4 records, like here, right? It's 50. So the number of records that I use in order to calculate the loss function is impacting my loss function. So it is getting dependent on the number of records. So today, let's say we have 10 records. We run our algorithm, we create a loss function, and we look at it. Okay, it is 15. Good. Tomorrow, what happens? We are we ran out of time and we should go home and all that stuff, and we stop doing things. Tomorrow when I come back, for some reason somebody who's kind has given me a few more data sets for my training, right? So I put them. So what happens? My loss suddenly it increases. So I'm like, okay, now I should chase 35 instead of 15, and I need to bring it down, right? The whole objective is to bring it down. So okay, I'll work towards it. I'll do something. Maybe I'll bring it down from 35. And as we get more data, the loss function will keep growing, and then we need to keep tweaking the thing. So loss function is not relative, right? It's not, I can't compare. In the first case also, my first equation that I had on the first day with 15 to second equation I have 35, 50, it's not comparable. So what should I do? I can't go with this, right? So what I'll do is I have loss for each of the rows. Instead of considering the sum of the losses, if I look at the average of these losses, it would be much better, correct? So for example, the first day, if I look at the average, 5 plus 10 plus 20, 5 plus 10, 15 by 2, it's 7.5. The average of the next day, it is 35, and it is 3 records. So it is somewhere around 11.66 or something like that. And the third date is 50, and there are 4 records, so it's 12.5, right? So this is average. Still it shows it is increasing, but that's the right thing, because um, that actually is more practical. But 15 to 35, 35 to 50 is actually a huge jump, but whereas 7.5 to 11.66 and 12.5 is actually practically correct, because the numbers are really the new data sets that are coming in, they're giving me more differences, so that's practically correct. But these numbers are more realistic, and they I can rely on those numbers than the individual sum of the numbers, correct? So we need to do an average of the loss functions, right? So which is the right thing to do. I'll This takes us something to our next so this is classified as loss function. Why do you have so many functions? I don't know, but people would have this is an evolutionary process, right? Like people had x and y, they put an equation. Okay, given equation, how do I see whether it is right or wrong? Okay, try loss function. They tried loss function as sum of differences. They've seen that the differences are the sum of the differences is not proper, right? It's being influenced based on the incoming data. It should not be influenced by the incoming data. It should not be influenced by the number of data set examples are there and stuff, right? They slowly realize. Then they said, okay, let's make independent of the sign, right? They applied modulus, and then they said, okay, based on number of data sets, it's influencing. So let's make average. Um, um, so that's how they evolved, and finally from loss function they came something called cost function. So the cost function, um, let's look it up here also. Explain cost function. Give an example. Yeah, so good. I think I should use this more than instead of getting tired on that. Okay. um, Question: why do we use squares in the cost function instead of using mod of the differences? Using the square of differences in the cost function, the mean square of ms squares, rather the absolute difference as in mean absolute error. Okay, that's MSCM. has our advantage in the context of linear regression and many other machine learning algorithms. Differentiability, squaring the differences makes the cost function differentiable. So as we said, so we in our flow we have arrived till here, right? 1 by m, that is, we said average or mean, and of sum of the differences. Okay. um, and we thought our equation is sigma I equal to 1 to m, and then we had modulus of yi and y predicted. This is yp or yp, right? Y minus yp. Modulus is what he said, which he uses the term mean absolute error, right? That's what we came to. But instead of using mean absolute error, the cost function uses here mean square error, MSE, right? So why is this a better metric than mean absolute error? So for that, he has people, again, they would have experimented with these things, um, and it works backwards also at times. That okay, mean absolute error is good. Let's move forward with it. In the further steps, when they go forward, they do other things, right? So loss function is just an indicator. Basing on the loss function, they should take some decisions with respect to, especially with respect to the algorithm, saying okay, the algorithm that we had, uh, 3x1 plus 3x2, again I think the picture is 3x1 plus 3x2 is equal to y, is wrong, so I should correct it. So how do I correct it? So I should change the variables. That are the variables are nothing but 3 and 3, right? 3x1 plus 3x2, I should change them. How do I change them? So these are the further steps that they do. But in those further steps, they would have encountered saying okay, um, the mean absolute error, if it's being considered as my cost function, the calculations that I do here is complicated. So how about I change the mean error? Can I change the mean error in a way that it actually makes my calculations easier? That's how people would think. So is it the right thing? The cost function being mean absolute error is correct. It actually represents the loss. You can actually look at it and then say, okay, you can compare in between different data sets and say this is how it's varying. But people make a choice. As I said, it's not only about whether it is right representation or wrong representation. It also boiled down to the future scope of using that particular, and where there's, for example, differentiability. So so squaring the differences makes the cost function differentiable, right? So that's one thing. So let's not get into the detail of it, but again it's more related to mathematical equations that we are going to go through later on. It makes it easier if there's a square. Okay. um, he says it has sharp corners. What does it mean? I don't know. Amplifies on large errors. Squaring the errors amplifies the large errors more than this. Makes more sense. Like, so what happens is 5 and 10 for us it looks like they're very, very close, but if you square them, what happens? One is 25 and another is 100, and so 100 sounds like a bigger problem for us, right? And compared to 25, right? So that's, they want to emphasize on the large errors, it seems. So that also makes sense. Mathematical simplicity, squared error function has nice mathematical properties that simplify the derivations of optimization algorithm and analytical solutions. Okay, again they're talking about derivations getting easier. Statistical interpretation, the use of square error and the cost function is related to certain statistical assumptions such as Gaussian normal distribution of errors. In linear regression, minimizing the squared errors is equal to maximizing the likelihood of observed data under the assumption of normally distributed errors. Okay, so these are all the reasons on further steps when they do when they a cost function, they take decisions on how the linear regression needs to be changed. We'll go through the other remaining steps also, but in those steps they observed saying, okay, if I go with mean absolute error, and if I do all the math calculations and all that to see the difference, for me it is getting complicated. So can I change this cost function without losing its context? That is, as I said, the number of data, the size of the data set or the individual values of the data set should not impact the cost function. That standard being kept intact, if we can change it so that the math becomes easier. Because again, the math goes into solving the problem, the solving this problem whole gets into computation, and that should be run on a computer. And that will take, if it takes more time, then what happens, you should wait more time for training your model, and that in turn takes more cost. So to avoid all that, people come back, say, okay, I want to reduce the cost. So people would have done all this and then like, dude, your machine learning is taking a lot of time, so let's reduce it. Then they said, okay, let me optimize it, right? So then they say, okay, where can I optimize it? How about my um, um, equation, fine tuning my equation or something like that? Could be, I could make it faster. Maybe the calculation should be faster. How can I make calculation faster? Maybe instead of using mean absolute error, use mean square error, and my calculation is faster. So I know I'm trying to give you a use case which is futuristic, but I think you guys should understand the thinking process of people and why they have arrived at mean square error. Okay, so those are the reasons why, instead of again, I need to stop and come back and then do this, but sorry for that, guys. Now if I open it, so what happens, the cost function in this scenario, oh, this is tough for me, but yeah, I'll just say 7.5 square comma 11.66 square comma 12.5 square. So the cost function is nothing but the sum of square difference between y and yp. So y and yp. Okay. So cost function will give us a metric to say, okay, if these are my points, this is x and y, and if this is the equation that I'm going to use, cost function tells me what is the overall loss if I use this equation as my model, this equation as my algorithm for training, and after training, if I deploy it as my model to predict y for given x, this is my loss, this is my cost that I bear if I do it. And people needs to decide, our data scientists needs to sit and data scientists with other people, they discuss and decide, okay, this is my cost function values and stuff. So this is the kind of loss that you will see if you use this kind of a model. Models are usually are like 80% accurate, 90% accurate and stuff. So when we talk of all this loss function and stuff, when you say 80% accurate, that means it is not 20%. It's not accurate, right? And even though 20, that means 20% of the cases, when the data comes in, it will give you something wrong, and there should be agreement saying, right, based on the domain use case that where you're using and stuff, you should agree on saying, yeah, I understand that 20% there will be mistakes, and my business can live with it, right? So, and both of them agree, and then to communicate this, like, what is 20%? Is it 20%, 15%, 5%? That is where this cost function will come into picture and say that that's the amount of impact, that relative impact that it has, and it will, if people are not okay with it, they try to reduce the cost function. The more you reduce the cost function, the more y and yp go closer to each other. So the overall prediction capability will also increase. Okay, so with that being said, we covered linear regression, with respect to what is the equation, how to calculate loss function, how to calculate cost function and stuff. But we didn't go to the next step, that is, how do I fine tune the algorithm and make it much better, how do I pick up my next equation? That's my first equation, which we think could be a random guess of what it could be. But how do I fine tune it to get an equation which is more closure, which reduces my cost? Everybody should use the same language, which reduces my loss or which reduces my cost. How do I derive to my next equation, which is closure? It need not be right fit into a y. That is not possible. Okay, everybody should be on the same page. It's not possible saying, okay, this is my cost, okay, let me change this and I'll make ypy. Not possible. You actually can go closer to it, but at times you could also go further to it, right? So these story of going closer further, how do you reduce the cost, how do you reach to a point where you say, okay, this is a good enough thing, I'll live with it for this particular use case and business problem that I'm trying to solve. This learning is good, this training is good, these inferences are good. These statements to reach, what do we do as the next steps? We'll cover them tomorrow. I gotta step out. Okay, that's all, guys. See you to Sumay tomorrow. Okay, and streaming. Bye for now.